Okay, let's see how we're going. We're live. Hello, Twitch. Okay, we got 2 hours to figure out the badge and make a Verilator simulator for it. We're not gonna have the buttons per se, but like at least the code we can run through operations. But there's a lot of documentation to go through, so let's just dive into it. So right now I wanted to see, there's a lot of, if you go to this HackaDay project right here, he has all the documentation if you want to follow along. So this is generic manual. Okay, so page 0 is general function registers, and page 15. Okay, the whole data contains 215, which gives a total of 16 pages. And if the half displays the last page, this enables both. Okay. I was curious about different opcodes. But I was curious about the memory 13. Yeah, we should go look at the data memory. I'm kind of curious to how that's broken out. Surprised there was only a total of 16 page. Okay. I'm curious about the data memory and the accumulators. Accumulators. We'll have to probably like look at a lot of details here just to opcode carry. What's 123? Okay, so it looks like there's, if it registers it or not. Stack pointer sounded interesting. So it can be used independent, which means only the first 15 data memory from page ones will be used. Okay, so page 1 or page 0? I think it's talking about page 1. So page 0 is the general purpose registers. Page 15 is special function registers. Okay. We're getting more. Stack pointer, good. Program memory, our program counter. Okay. Okay, jump relative to the next location. Okay, add on stuff, input output connector. Okay, cool. There is data memory. Oh, program execute from 4K program memory. Cool, that's what I want to get to. Can the data matrix show program memory? Um, Data memory. No, the auto clears all program and but not the content saved in the flash. Okay, so when these modes up here, we had program memory address, program. Okay, so in program mode, we have memory addresses, or program memory addresses. Can we change what's viewed? That's gonna be interesting. Hey, Casey. Yeah, I will be talking at HackaDay SuperCon. Okay, we have programmer's model. It looks like cool. You can see the out and in. Weird. PC history pointer to do. Okay. How big is it? So it is by 12. So is there an easy way to look at it? Okay. Okay. Modes. Temporarily editable. Okay, I like this one. Okay, so okay. Page 40 can be used to for a select number of main or from page. Okay. So page 2 to 13 are user. We need to figure out how to access them. Okay. Okay, it's direct mode. Single step. I'm trying to figure out how you get program. Okay, so it looks like we have to be program mode to be able to access. Okay, cool. Okay, so we should set the 12-bit program word. So 12-bit right here, this one right here. Okay. Is there a way to display it? I'm curious. Okay. Program. Delete the current run. There's no undo. Okay. Okay. Anytime the program address. So it's loading it into the opcode. Okay. Writing 0 to the register switches the unit momentarily. Okay. General purpose data RAM. Okay. Um, System program memory. Oh, we have different flash storages. And then we can save the flash. So if you, okay. I'm curious now. So I think that's with the processor though, not with what you're doing. Not with, this is with the big processor. This is from the system processor, not the hypothetical simulated processor. Yeah, that's what I thought. Okay, cool. Now let's go dive into the instruction set. So we have three different types of codes. We have two operands are not used, but we have two sets of operands. Here we have 8-bit code and one operand or two operands. Okay, we gotta figure out where the accumulators come into play here. Still, if everything but the accumulator is making sense to me. Okay, in the first phase, Okay. Let's see if the accumulators are referenced here. Add the contents of register RH to the counter place the register RX. See, otherwise reset. How do you enable that? Here and save. Okay, makes sense. Add with carry registers. Adds the contents of register RY plus the contents of the carry flags to the contents of RX into the register. Register direct addressing. If underflow, otherwise set C. Oh, okay, that's what it's meaning by that. No subtract. Any special these two subtracts? R6, R2. Oh, this is bringing the out. I'm a little confused in this, right? So I guess we're just updating the out then. Subtract register from with borrow. Okay, minus inverses C. Or that's pretty basic. And trying to figure out where the accumulators come into play. XOR move. Okay, I'll keep my eye on that. Moving a register, pretty basic. Oh, we got two things right here. Move register to register and move literal to register. Okay, so it's moving a literal value. Okay. Move contents of register RO to the data memory addressed by RX and RY nibble into data memory. Assuming that it is page, or is RY? So RX is page. And that R4, R7 goes to 001. Okay, so help me here. Where are you going? 110 into data memory. Okay, yeah. So page 1. Okay, got you there. Move the 4-bit contents. The contents of data memory just by to register 0. Okay, so we automatically move the value to. Okay. Move the contents of data memory by literal. Okay, that's the easy one. You can do literal that way. Easy peasy. Move. Load ableist to registers. Okay, keep going. Or move the contents into the PC. Okay, works. Jump jump relative, right? So program counter plus and unsigned, but also +1. Compare register with 4-bit literal. Okay. Add 4-bit literal. Okay. Increment register by 1. Decrement register by 1. Decrement register, and if the result is 0, skip the next instruction. That's a nice jump command. I don't think I've seen that before. That's a very good loop. Great for loops. That's a good loop command. Or with literal, okay, and with literal, XOR with literal. Does it just double increment the PC counter? I want to go back to this. Oh yeah, double increment the PC crown. Exclusive or to do exchange n main register from pin 0 with page E. Oh, so this just grabs a bunch of them. E. Okay, yeah. Bit test and register RG. So that's bit M. Okay. G and M. Register RG. You only get what, 4 picks, and then you can do a single bit. Bit inspect, test, register bit. Oh, continued. Special case G equals 3. Where does it talk about that? Okay. So it looks like you can do the input. Special case output. Okay, yeah, it looks like you can read, inspect those bits. Clear bit and register B. Special case of the output. This toggle bit M. That also an output bit. Yeah. Also, what's got here? Rotate right through carry the register RY. Rotates the contents with carry. Okay. Return from superstring with literal and R register R0. Load R0 with literal value N and pop PC from stack. Oh, so that's the return value. That like load is 0 or 1. Okay, literal N. Just all we're doing. Okay. Skip the next. Wow, that's interesting. Okay, so condition is true. There's 4 instructions. zip code are the condition codes. See the condition table. Gotcha. Okay, that makes sense. Okay, so we just speed ran through all those instructions. We can create a simulator if we have time. We got 30 minutes. I'm gonna see if we can figure out the accumulator. We got essential function registers. Special function registers. Was there anything about special registers here? Okay. Um, oh, okay, that makes sense. N, input counters, okay. Okay. Cool. Where are these registers? Those one. Program jump. Okay. Medium high. Special function registers is on page 15. Do, okay, let's see. Clock. Simulated clock divider. Okay, we can pick different speeds. Oh, you can go really, really slow. That's fun. Function ranger. Okay. So fixed on using the user sync flag. Guess we gotta get to the user sync to understand that. Okay. Okay, so it's just a interrupt, I guess you can pull for. Right, there's nothing about sync in here. Nope. 960 We should have that as the default baud rate. Oh, so you can actually send serial over. Okay, let's go back to this. Okay, cool. So you can have UART going during operation. There's this whole part right here. You can still communicate during operation. Receive contains. Um, that's the auto up. Alternate latch. Register RS3 contains standard RS1, 2 bits RS. Okay, interesting. Okay, keep going forward. Oh, okay, so you should be able to see. A key reg. Okay, that's the value. Dimmer. Oh, we got random number generator. Cool. Um, add. Okay, this has accumulator stuff. We should look at this. Okay, I'm curious. Ask do the contents for and place the content in X. Okay, where does the accumulator come into place? Um, do contents X and Y. Okay, let's go back to direct mode. Oh, you can press the clock, I guess. This is 3 and 13. To give you 16, which causes there to be a carry out. Eight and 6. Oh, you bring it over. We have a clock. So this direct mode. Okay, so the accumulator only comes into effect for the direct mode. Hmm. Oh, and here is register X. Accumulate. Okay. 15. And the carry. And figure out how the accumulator works in this situation. I guess it's not terribly important. You want to OR that, we get that value, which is right, and 9 and 3, you get the 1. Exclusive OR. It's an accumulator. Move. Okay. Okay, so you can play with the number thing in direct mode. Okay, anything. I think we're good. So I think it's time to generate our um opcode tables, and let's make a simulator. Okay, we're gonna go to type hack E real quick. So we had opcodes. I said opcodes 4 and opcodes 8. Yeah, let's need like a good instruction set. Okay. 4, we're gonna go add 4 bits. 0, 0, 1. And then we're going to do a bunch of these. This is gonna be 3 bits. And it's just, gonna 1, 0, 1, 4, 5, 7, 8. Do we do zeros for that? Or just do second? We can just do, if it's all zeros, we should be able to tell. Okay. Then this, depending on the opcode. Do okay, we got ABC, E, yes, we have internal memory and program memory. So let's go. I want back here. I want to look at go back to single step. I think it does read the memory. Program. User sync. Yeah, so there is sync in here. Okay, so there this is where it talks about the user sync. Okay, back here. Um okay. One programs the current is informed on the buttons. Do you press the result the current option flags or legends master the flops of the accumulator status register. Okay. After the step button is released, new value of the destination is moved into the destination. Hence, incomplete one and the contents pressed button is red and launch displayed in the okay, cool. Cool. So you can play around with it. Back to instructions. And exclusive or ooh, we have move. Move. These are all moves. Okay, moves. I'll have to figure out a smart coding for that. And this is they are. Okay. And then we're gonna copy this here. And we have space CP. This is just add. R0. Okay, it's in this section. It should be fun. Increment. Decrement. Oh, this is a fun one. The skip if meets flag condition. This is or literal and literal or literal. Any other ones? We gotta put like a 0 there or something. Where's the, we have a spacer anywhere? Okay. Okay, we can work with this. What's after and fresh? Oh, that one does. So figure it out in a second. Okay. It, this is be set, be clear, space P. Okay, did I do this right? If CP and ink deck DCZ 100. Oh, there's a 0. We should just gonna change everything. Oh no, we'll just easiest way to do that is where do we stop? Right here. I think there is easy way to do that. And this will be RC return the beautiful. Okay, cool. Okay, then we can get rid of all of these. And we have to do some packing of the 3 different types. And it's basically so it would be RSY and RSX in the opcode. That is going to be, we'll say A, B, and C. A type, then we have the B type, which I'll call register Y. Register Y. Then, oh no, these supposed to be 3. 3, 3. To be zeros. The B type, and I'll do the C type. And the C type, we're just going to split this into RS, M and RS B. B and M. And that's all. And then we can delete these. I'll just do A, B, C. Okay, cool. Now we can get our processors working. Ugh, got a lot of instructions we gotta do. Okay, so we have a clock, we have the instruction. Um, we didn't read any program. There's no read data. There's no saving. It's all data memory, and the program memory is ROM, so you can't operate on them. So what do we do? I guess the PC would be important. We're gonna have just the instructions. The instructions what you're loading in. No, we're gonna have inputs. I don't know. We just call it in. You want to say input in. We'll say in reg. Okay. There's no enables. None of that. I believe this is all. We have the instruction in, and then we have these. Okay. Um, we don't need any of that. Initial PC is 0, I believe. Might need to retry this in a bit. Okay. So our registers are only 3 bits, and there's only 15 per page. Cool. Yeah, that seems doable. Right. Um, so these moves were the only thing that could access the user data area. Okay, what was no. So we have moved the literal into the PC counters. Move literal into move contents is right here. Move R0 into any of the registers. This is still going to be 3 and 3. Initial PC is only 12. But yeah, cool. PC plus 1. We're probably gonna have to take all of those. Okay, so we have a unique cape. Oh, you know how we can do this. Okay, going back to type pack, we're gonna have a 0. And we're gonna do, we're just gonna say type A, type B. And that's gonna be the 0, 1. And we will so this is opcode for opcodes. Oh no, names. Opcode A. I don't know. This is opcode. We see it that way. But is it still 0? This situation. 8. So we just put that there. Okay, okay, I think it works now. So, boom. Okay. Um, so we're gonna have I type. What's this gonna be? A type. And so the first case, type B, we're going to for the default. Okay. We're gonna do this one last. Go back to my make file, right? Was there just a Verilator one? Um, okay, we'll have to write a very simple instance for it. Okay. Um, yeah, let's go ahead and write a simple instance for it. So we're gonna do. I can just pull this up as something. In case. I think that's what we can do. Yeah, let's try it. That. Okay, cool. We have a very simple module. And we're going to try to make a Verilator. So in CPU test bench, we have we'll have to do that later. So all we want to do, yeah, trace false, cool. Um, wait, execute. Don't worry about those at the moment. We don't need no instruction. Make it really small. Um, and don't care. We just want to make a CPU. I guess we'll just do the evaluate. Earlier, right there. Okay. Oh, I think I have to make those. Um, But going back to the make file, we're going to just do those for now. And open a terminal. And we're gonna do cd build make cd and make CPU. Okay, let's go fix type pack. It's a legal character on line 4. Oh, am I missing a B or B? Okay, what did the original one look like? Go. Oh, I did the wrong direction. B. Make CPU. Okay, cool. 77. A, B, C. We need C right there. Make CPU. Unexpected default call. So let's go Verilog unique case. It's been a while. Okay, so we go back to here. I think it wants all of them. So I guess let's go ahead and specify all of them. I don't think you have to say anything. But let's try. So move to our split left, right? No, that's not what I want to do. Just put this over here. Okay. Fourteen to 28. There we go. Is it happy now? Line 14. Oh, I think it's unhappy about the space. Annoying. Oh, okay. Is there a unique case where you just pass? Thing? Okay, so we do make CPU. Are you happy now here? Unexpected end case. Okay, it just wants us to do something. let's just do it. Add, right? Let's get the ad doing something interesting. Okay, so we have let's do the and. Okay. And so in the and we're doing this. And what we're gonna do inst rsx, right? Instructions, give me the and. So yes. We also need a 0 there. Boom. A type rsx. A type sy. Make view. 25 and 5. Not going to like that. This is going to have to be immediate. We do n. They do n for these. Explosive or n. N. Okay. Make view. Okay, we made it. Cool. Let's see, Verilator. View top 8. Where is 8? Oh, okay. 12. Sorry. Oops. Make view. 12. Okay, we'll just do D. Okay, so casing complete. It's that's fine. Okay, so we are emulating that function. Let's do some other ones. Okay, you need to move. Yeah, there. Okay. Or is this gonna be the carrot in this situation? I think it is. Let's see, make CPU. Okay, we're happy. Type B, we're gonna type the end. Okay, let's go check if we're supposed to do anything with the flags. I don't like the flags, but we'll have to do stuff with the instructions. And if result is 0 after set Z, otherwise reset Z. That we need what's our little, might as well stop at the start of the top. Plus carry. Okay, Z. Okay. CZV. Z, Z, and Reg B. May not be happy with those names. We'll put flag underneath. C is used for other. Okay, make CPU. Okay, cool. We need to do the if right here. Like this little fancy if. We're gonna say if let's go back to, I should just, I think it was 0, right? If it was 0, then the D flag. Yes, I know one. Is that the case? And okay, that one. Otherwise, reset. Else. Make you. Oh, I think we have to do begin or end multi-line one. If it carries over, yeah, we need to begin and end. Begin. Just do that. Make CPU. It's happy with that. In the instruction, exclusive or does the same thing, does or do the same thing, or does the same thing. So we got or the and the exclusive or. Now let's do the add. And the add. How did we do overflow before? Overflow just not considered. It's not. It's interesting how simple of a RISC-V processor you generate. Okay, so now we're going to do we're just going to add the two registers together. We'll need to handle some special cases. Okay. So now let's go consider the flags. Least we screw up. Okay. Since it talks about it pretty straightforward. If there's an overflow, let's literally write that out. Right. And set the C flag. Are you happy with I don't really care for the simulation. Oh, art, what? Yeah, this is maybe A type, A type, A type, A type, A type, and this needs to be what, RSX, the RSY, make. Okay, it's happy with that, right? Okay, set C flag, otherwise Z for signs if there is overflow. Okay, how do we do that? If it's signed and there's overflow, that's where positive numbers. Okay, signed element. Basically, if there's a 1 up front, but if there's overflow, we're adding. Ooh, how would you do that? We changed it. So this needs to be. This need to be computed before. Seems silly. Do it afterward. Ooh, how do we do the flag? How do you, if there's overflow, you would want to compare bits. Yeah, I'm gonna look at figure that out. Yeah, we're all happy. Okay, let's go to ADC. And it looks like identical. You're just adding. Oop. So if ry is 0, x is greater, to do other ones for some. I gotta figure out how to do maybe the old flag. This need the C flag, but we need the C flag here. But we change the X value. I think that's okay because this is we're not updating until the end. These are non-blocking, right? Verilog blocking versus non-blocking. I can never remember which. Blocking, non-blocking. Yeah, we're doing non-blocking. So we can do these in any order. These values red will be the old ones. If that's the case, we'll calculate the flags afterwards. It makes sense. Okay. Doing the subtract. Just see if some of these work. What's a good one? We need I guess we could do the move. We could do the move immediate and just see what we get. Okay. Let's try to do the immediate one. That in a second. Grab that. I can't figure out how to do the B. Okay, and what's this sub BB? Sub with subtracting the carry RY. So it looks like the same thing. Just so I say we grab this one and do a subtract and a subtract. Black should be fine. Okay, let's do the move. Which move is an interesting move? Move to register RX. Yeah, let's do this one. So that's going to be move one. Move one is very basic. We're just going to Y. Right? Yep, move. Move. No, nothing else. Okay, so I think we should try to see look at the GTK wave of this. Okay, so we're gonna have to go look at the. It's been a while since I've done Verilator. Let's go look at the test bench. Right, so we have all this fun stuff. We have Verilator, we have the clock. Final. So we created H file right here. CPU, be like a CPU H, right? Okay, so let's grab that right there. I'm gonna go to test bench. But we are going to delete this. For that flips the clock. That's a clock period. Okay. So we do this. We have to set the instruction. How did we set the instruction? Yeah, so we just need UTD instruction. Okay. UTT right here. We want to do a move. Okay. Copy. So let's do an instruction right here. So it's gonna be an 8. And then we'll do, so we're gonna do 8 register 0. Here we're gonna do register 1 and close up. And yeah. And we're just gonna make CPU run CPU, and so we should have to be CPU ls. We should have a GTK wave here. Where's my VCD? What's the VCD? It'll be CPU dot VCD. I don't see it. Oh, I gotta do it true. Do true for that one. Make CD that. Make CPU plus. So we use CPU. Okay. Now I need a GTK wave. GTK wave, open BCD. You know what was the simple instruction? GTK wave, path to BCD. Okay, so do we have GTK wave? Let's open it from here so I have this. GTK wave. So sudo at GTK wave. I got 30 minutes. Much time. Okay, so we want to go right here. You. So we want to do GTK wave and the CPU dot BCD. Right here on this screen, I'll bring it over. Okay, so top. Append. Okay. Didn't like our registers. Yeah, the registers are acting weird. Okay, so let's go fix that. VS Code, CPU top. Okay, multi-dimensional array in Verilog. Oh yeah. Oh, okay, cool. So my bad. We wanted it on that side. CPU. Oh, so yeah, there's gonna be 15, 15. CPU. So 19. Oh, yep, my bad. We gotta go add a bunch of these. Do, do. It's there. Okay, that should work. Okay, so we do CPU, close out GDK wave, and then open it again. It doesn't like our register. Why doesn't it like the registers? Hmm. Should we? Why is it not like? What if we just remove that real quick? And then we just do a control, find and replace all of that. We might have to do special registers. Okay, cool. Um, so this instruction, we're writing that to 0, and we are not. So let's resolve that problem real quick. So we're doing move 1. What is move 1? Move 1 is that reach group. Okay. Back here, did we? Okay, so it is 9. Go back to CPU test bench. Okay. We could just have to do the address some other way. We'll figure it out. Okay. We'll try to do the basic instructions. Then not the correct op code. Are we not doing this in the correct manner? Um. Okay. The decode not working as I expect. A type opcode. So pick the instruction, cast as an A type. You get the opcode. Guess we'll just have some registers real quick. Info A. B. Okay. So let's see what we got here. So we have an F and a 9. We did these the wrong direction. Okay, so fix that. We're gonna go back into type pack real quick. And exchange. Right. Okay, cool. Now we do make CPU, cast it, call it, then go here. Did we change our register value? Open big. Yes. Yes, look at that. Working. Okay. So we got that function working. Let's do an add real quick. Just add those two values together and see what happens. So yeah. Do that. We're gonna do that in the test bench. Let me make this cleaner. Okay. So we're gonna do an add R0, R1. Do that. Go look at cheat sheet. Add is gonna be a 1. RX is where it's being saved, so something like that. Okay, then cool. That works. And the carry flag went high. Okay, we got a few minutes. We could try to work on the remainder in here. Oh, how are we gonna do the register? Guess we could just do, what is it, 256? We could just, do like 5. What happens to if we do make 50? Will it complain? Um, we run it. This will be fun. I think we might have to think about how we do that. Because now if we open in this, doesn't even have them. Is it not like it must have a limitation signals. Interesting. It doesn't like that. Oh. So I guess we'll just have to do general purpose register, special registers, and stack at other values. And the generic memory. General purpose range. It doesn't like them. Rough. They're there. Let me see. We open up the VCD. Try that real quick. It'll be nasty, but I'm curious. Do fresh. Soft res bench. Use UVCD and wave. Yeah, it just looks like the V's. You guys can't see this. Move to a new instance. Yeah, it looks like they just didn't record all these values here. But there must be a limitation. There is it specify in here. Okay, that's in the UTT trace. So go to CPU. CPU.h trace levels. Okay, yeah. Verilator trace not working on large trace. Oh, is it because how am I dumping? Do do do. Yeah, I don't know. We race 99 levels. We dump it. Yeah, I don't know. They just have this random race level 1 under T. Okay, what was that? I gotta go find out. We have a subscriber. Right. Um, thanks. Thanks for joining. That, what did that? Yeah, better to keep it. If you want to say something, send it in chat. We can talk about Verilator, HackaDay, processors. Hmm. So, I don't know what the. Okay. PCC large memory. Verilog. Add the flag. Um, guess you do pay. That'd be interesting. I want to try that. So we go back here. We'd have to. Oh, it would hate us. It would hate us so much. We just say current page equals. I like this idea because it suggests the behavior. What are you unhappy about? Let's do this. Ugh, I don't want to put them all in. But we could just, yeah, let's F. Boom. Replace. Replace. Okay. So would you make CPU? Um, what? Kill this. Run it again. What will it look like? Oh, current page. Cool. End. Yes. That's cool. I wish we could like reduce these sections. BCD is still not the best way. These. So we can have current pages, next pages. Is there anything in the make file where we erase? Let's try the This is chiseled though. Okay, so that's probably the best way. We'll probably have like a current page and what, like a next page, right? And the next page be like, I have to make a little counter so you could like go through them. Good. It's based on the that would be nasty because it'd be the last page 0 bit, right, and this would be that plus 1. Make it. I'll make you. You still do it. Oh, that's funny. Okay. Close that. Then it again. There we go. Next page. And page. We'd have to write with that special register. Okay. Whew. So I think this is a good place to stop. We have emulated a few of the functions. I'll have to go through and do the rest. I wonder if I'll have time. But yeah, great way to emulate it. Can't really push this at the moment, right? Branch. Yeah, we'll keep it as is right now. Okay,